Hi, in this video, I'll present an introduction to linear transformations. This will be a full lesson type of video, so it'll be a little bit longer, but also there will be a lot of times during the video, I'll pause for you to do math, so the video will have a certain interactive components as well. I'll be covering three things. Number one is a motivation for and definition of linear transformations. Number two is I'll prove some important properties of linear transformations, and you'll be able to practice writing proofs in that part as well. And number three, I'll talk about the geometric meaning of linear transformations and how we figure out what a given linear transformation does geometrically. You may see that the material covered in this video is roughly equivalent to section 1.8 in the Linear Algebra book by Lay. All right, let's first get started with an example of a matrix multiplication. I have a matrix and I have an arbitrary vector xy. Let's multiply it up. This matrix is 2 by 2. It has 2 rows and 2 columns, and the vector is the same as a 2 by 1 matrix. The inside numbers are the same, so the multiplication is well defined. And the answer will be 2 by 1 based on the outside numbers that we see there. So the answer will have 2 rows and 1 column. The first number on top will be this first row dotted with this column. And therefore, it is equal to x. The second position will be the second row. So I dot them together. And the answer is negative y. Let's say that I call this matrix A. Then I have A times xy. Any arbitrary vector xy is going to be equal to a new vector that has the same x value and the opposite y value. Let's take a look at it in the xy plane. If I start with any xy vector here, and I apply this A matrix to it by multiplying, then I will end up with the x negative y vector down there. And this is true for all xy vectors. If I start with that other xy vector in the back, I'll end up with that other x negative y vector down there. Also true if I start with a y that is below the x-axis, then I will end up with an x comma negative y that is above the x-axis. For each of these vectors, by multiplying matrix A to it, I get an image of it that is the reflection across the x-axis. This multiplication by this specific matrix A transforms any given vector into another vector that we call the image of it. And so this is the motivation for linear transformations. We want to study all the properties of these kinds of transformations. If I want to start with a vector and transform it into something else, what can I do to get that? And what properties I get out of it? That's the motivation. Right, so now let's define linear transformation. I'll do that by defining two things. First, I'll define what a transformation is. And then I'll define what kind of properties must a transformation satisfy in order to be called linear. A transformation also called a function or a mapping. And let's denote it by the letter T. Let's say that we go from one Euclidean space to another Euclidean space. Let's start with a vector x in the starting set, and then gives you a result, a different vector in the ending set. So you see that it's very similar to a function in regular algebra. In regular algebra, you take a function, you take a number x in some set, usually the real numbers, and then you assign it a value, f of x, y equals f of x in another set, usually the same set, real numbers. And that's the definition of a function. In algebra, this is a definition of transformation in linear algebra. And the way we write it is like this. We say that T starts from the set Rm, and it goes into the set Rn. So we draw it with a regular arrow like that. And then we talk about the specific item x, specific vector x in Rm. It goes into a vector y in Rn. And for that, we write it with an arrow with a little tick mark at the beginning. And this thing here is called the image of x. And note that the image of x is sitting in a different space. M and N may be different, so you could have a 3-dimensional vector and somehow transform it into a 4, 5, 6-dimensional vector if you want, or a 1-dimensional vector if you want. In this case, we call this the domain of T, and that's familiar with the word domain of a function in regular algebra. And the space that we're arriving inside of, we call it codomain. It's not a range yet. The range is this. The set of all the images, that's the range. The set of all the T of x, that's the range. Let me show you the difference by using an example from regular algebra. Let's take a function f that goes from the real numbers to the real numbers. That is defined by f of x is equal to sine of x. In other words, I start with the number x and I send it to the number sine x. Then in this case, the domain would be R. The codomain would be the other R. And the range, though, is not all of the other R. Sine of a number is only between -1 and 1. So the range of f is only the interval from -1 and 1. Right? That's the difference. Now, the reason why we didn't use the word codomain in regular algebra, because we really didn't care. It wasn't important to us. In linear algebra, it becomes important because we wanted the arriving set, the set that the range is inside of, that big set, we wanted to have the property of what we call a vector space. So we start paying attention to the big set that the range is in. When we were doing regular algebra, we really only care about the domain and range. All right, that's the definition of a transformation. Now let's define a linear transformation. a transformation T is said to be linear if and only if. And by the way, this is shorthand for if and only if. If and only if it satisfies these properties. There are two of them. Number one is that T is additive. So what does it mean? It means that if I have two vectors over here and it has a sum, right? So the left-hand side is a transformation of this sum. I take this sum and I transform it into something else over here. If T is additive, then what I could have also done is instead of adding over here and transform, I can transform these two separately. They become whatever over here, and then I could have added them afterwards. Okay, so if T satisfied this, is said to be additive. And the second property is what I call scalar factoring. It's also called homogeneity, that the transformation is homogeneous. But in a typical differential equations and linear algebra combined class, the word homogeneous comes up in so many contexts that using it becomes confusing. So for this video, I will use the word scalar factoring. But I will note that the official name of it is that it's homogeneous. And it says that for any scalar C, if I start out with a vector U, and then I multiply it by C, so I end up with a longer vector, or maybe shorter or opposite side. But let's say longer vector. And then I want to transform this C times U. I will end up with some other vector over here. Well, this property says if T is linear, then what I could have done is I started with the original vector, transform it first, and then multiply later, and I should still get the same answer. And this is a definition. I'm boxing it up. Throughout this video, I'll refer to property 1 and property 2 pretty often. So property 1 is the additive property, and property 2 is the scalar factoring property. I can factor out the scalar C. All right, I started this video with a matrix multiplication. So let's take a look at matrix multiplications and see what it has to do with this whole linear transformation thing. Let A be an M by N matrix, and I take this A, I multiply by a vector. The matrix A is M by N, and therefore the vector has to be N by 1 in order for the multiplication to make sense. And the result is another vector, and this vector will have to be M by 1. If I'm going to call this a transformation, then it has to go from this space, and it will result in that space. So T will have to go from Rn to Rm. And I define it as T of a vector x. Take the matrix A and multiply by that x. I'm going to prove that this T is a linear transformation. Well, what does it mean to prove that something is a linear transformation? A transformation is linear if and only if it satisfies these two properties 1 and 2. So to prove that something is linear, I have to check and make sure that it satisfies 1 and 2 both. Maybe I should add the word and here to make it very clear. I've been saying it, but I have not been writing it down. You have to have 1 and 2 both. If you have one but not the other, you're not a linear transformation. All right, so to prove that T is a linear transformation, I'm going to have to check the two properties. If T satisfies both of them, it's linear. Otherwise, if it fails one or the other or both, It's not linear. Let's first check property 1. This is property 1 that I need to check. What is this left-hand side? I define T as multiplying a vector by the matrix A on the left. So this is A times this. Whereas on the left-hand side, the first term is defined as A times U. And the second term is defined as A times V. So the question is, are these equal? Yes, they are. We know that matrix multiplication is distributive. And therefore, property 1 is satisfied. All right, now let's check property 2. Is this true for all scalars C and all vectors V? Well, the left-hand side is equal to A times this vector. And the right-hand side is equal to the scalar C times the T, but the T itself is defined as A times U, so AU. Are these equal? Yes. We know that this can be done with matrix multiplication. So this is also satisfied. Our transformation T satisfies both properties, therefore it is linear. So this T is a linear transformation. What is this T? This T is defined as multiplying a vector by the matrix A, any vector. And is there any restrictions on A? No. A is any matrix that fits the size, right, of the multiplication. So this actually means that we have a rule that says that matrix multiplication is a linear transformation. This is a very important rule, so I'm going to box it up and put it aside. We actually have a name for it called a matrix transformation. Let's do a couple examples from regular algebra. If I think of fx equals 2x as a transformation from the real numbers to the real numbers, then is f a linear transformation? Go ahead and try it. Do the same thing I did before, check it against property 1, check it against property 2, and see if the conditions are met. If the conditions are met, then f is linear. If either condition is not met, f is not linear. Right? Go ahead and press pause and try it and come back when you're done. All right, welcome back. Let's go ahead and check the two properties. Property 1 is that f of a sum, is it the same as the sum of the f's? Well, f of x plus y is equal to 2 times x plus y by definition. And oh, look, I can distribute this. So it is 2x plus 2y, and it is indeed the same as fx plus fy. Yes, the first condition is met. What is f of cx? By definition, is 2 times whatever is inside the parentheses. So it's 2 times cx. But then this is the same as c times 2x, and c times 2x is c times f of x. So yes, this is also met. Therefore, f is a linear transformation. Great. Let's do another example from regular algebra. Given this other function, g, also from real to real, and g of x is 2x plus 1, is g a linear transformation? Go ahead and figure it out. Press pause and come back when you're done. The answer is no, it's not. If you didn't get no, go ahead and try again. Right? Press pause and try again and come back when you're done. Okay, welcome back. Let's check the conditions. Condition 1. Is G additive? Well, on the left-hand side, I have 2 times x plus y plus 1. That's the left-hand side. That's 2x plus 2y plus 1. On the right-hand side, I have 2x plus 1. That's the g of x. And I have 2y plus 1. That's the g of y. Add it. And they are not equal. And since they're not equal, g is not additive. Therefore, it is not a linear transformation. The answer is no. Wait, but 2x plus 1 is a linear function. Mx plus b, 2x plus 1. Yeah, it's a linear function in regular algebra, but it is not a linear transformation in linear algebra. Linear transformation is a new technical term that does not necessarily mean the same thing as linear function that you learned in regular algebra. Okay, so be careful of that. By the way, in this case, I already checked property 1 and G didn't meet property 1, so I don't have to go on anymore. But just for fun, just in case one of you used property 2, I'm going to show you how property 2 is going to work in this case. Property 2 is scalar factoring. On the left-hand side, I have 2 times that plus 1, which is equal to 2cx plus 1. But on the right-hand side, I have c times 2x plus 1. And this distributes into 2cx plus c. And so they are not equal. They're supposed to be equal for all c. These two are not equal for all c. They're only equal coincidentally at one spot when c is equal to 1. So that doesn't count. So again, based on property 2, G is not a linear transformation. It is a linear function, but not a linear transformation. All right, let's go back to the world of linear algebra and vectors and the spaces they are in. Let T be a linear transformation, T going from some Rm Euclidean space to Rn Euclidean space. The question is, compute T of the zero vector. I think you're able to answer this question on your own, or at least try. Let me give you some hints. We're given that T is a linear transformation. That means T satisfies conditions 1 and 2. So take condition 1, take condition 2, and put in some specific values in it to have a T of 0, and then see what the answer is. Okay, that's the hint. So go ahead and try it. Press pause and come back when you're done. Okay, welcome back. We have 2 properties, so I'm going to use either of them. I'm going to start with property 1 first. the additivity property says that T has to satisfy this equality for all vectors U and V. How do I get a 0 out of this? Well, I'm asked to calculate one of these, so I'm going to try to put it in there somewhere. So, you know what? Let's put it there. Then what does property 1 become after we've let U equals 0? We plug it in and we get T of 0 plus V. Well, 0 plus V is just V. T of 0 is T of 0. And T of V is T of V, which I can subtract both sides. This becomes 0. This also becomes 0. And therefore, T of 0 is equal to 0. There's the answer. All right, just for practice, go ahead and do it again, but use property 2. See if you can arrive at the same answer by using the second property, the scalar factoring property. Press pause and come back when you're done. All right, welcome back. This is the second property. How do I get a T of 0 out of it? Well, I can do U equals 0 again, right? That will get me a 0 right here. C times the 0 vector is the 0 vector. And now I combine like terms. I put this over here. Okay. I have T of 0 right here, what I want, but it's being multiplied by some number. So the most convenient thing for me to do is make this number into just 1. And to do that, I set C equals 0 because C, this property here is supposed to be true for all scalars C, so I can just pick my scalar. If I pick my scalar C equals 0, then this is equal to 1, and I have T of 0 is equal to 0. Box it up again. All right, this property is actually more profound. It has a deeper meaning than first appears, because this 0 here is in the Rm space. And that 0 there is in the Rn space. So this property actually says that if T is a linear transformation, then you start out with a 0 vector of this size, and you always end up with a 0 vector of a different size. It's also deeper in a different sense. If you flip it around, any linear transformation has to take a 0 and arrive at a 0. Any transformation that takes a 0 and does not arrive at a 0, then we know it's not linear. So it actually becomes a very quick way of checking if something is not a linear transformation. So let's write it down as a rule. Box it up. Given a transformation T, if T starts with 0 and end up with something that is not 0, then we know that T is not linear, not a linear transformation. So if you look back at the example we did earlier with regular algebra, g of x is equal to 2x plus 1, then yeah, when you plug in 0 here, you don't get 0 there. It may be a linear function in regular algebra, but not linear transformation in linear algebra. All right, let's now prove some important properties of linear transformations. I'm going to write it as an example, as an exercise. Let T be from some Rm space into Rn space, be a transformation of some kind. We don't know if T is linear yet. This exercise is gonna talk about that. Prove that T is linear if and only if given any two vectors UV in the domain Rm and any two scalar real numbers CD. Actually, let me write it as scalar. Then this property is satisfied. Basically, this property says that if you're given a combination, a linear combination like this, a combination with just constants and addition, you can expand it all out, kind of like algebra. Actually, let me go back and do something else before we continue. This property is very important, so I'm going to number it number 3. And this property that we're about to prove right here, I'm going to call it number 4. Let's prove this. But before I prove it, actually before you prove it, let me explain what it is that we're proving here. We're proving an if and only if statement. So that means we have to go from here to there and also from there back to here. We have to go both ways. We have to go from T is linear to this number 4. But what does it mean for T to be linear? For T to be linear, it's 1 and 2, right? Property 1 and property 2. That means we actually have to prove 3 things. We have to prove that if we have 1 and 2 both, then we can arrive at 4 as a result. That's one direction. And then the other direction is that if we have 4, then we have to result in both 1 and 2. But that's an and, yeah? So that means we have to prove that if we have 4, we will result in 1, as well as if we have 4, we also result in 2. We have to prove all 3 things, this, in that. Yeah, okay, so you're totally capable of at least taking a shot at this, so go ahead and try that. Do this line first. Prove line 1. If you're given properties 1 and 2, you can arrive at property 4. Press pause and come back when you're done. Okay, welcome back. Let's prove this line. Well, I'm trying to prove number 4 here, and number 4 has a left-hand side and a right-hand side, so I need to prove that they are equal. So I'm going to start with one of them and see if I can arrive at the other. I can start with the left-hand side and see if I can arrive at the right-hand side, or I can start with the right-hand side and see if I can arrive at the left-hand side. I'm going to try this. Okay, T of this. Well, this is a sum of 2 vectors. And since I'm given that 1 and 2 are true, I can apply property 1 and break this sum into 2. Oh, now I have a scalar multiplication here. So that means I can factor it out by property 2, which is the right-hand side. So I'm good. If you start with the right-hand side, you can probably do the same thing backward and end up with the left-hand side. So either way, the first line is proven. Great. Go ahead and do something similar like this and to prove line number 2 and prove line number 3. Press pause and come back when you're done. All right, welcome back. Let's prove line 2. Line 2 says if I have the equality that is property number 4, I can arrive at the additive property, meaning I'm given this. And I'm trying to arrive at this. What's the difference between them? Well, the difference is that this line has these extra numbers and that bottom line doesn't, right? How do I make the extra numbers go away? Ha! Since C and D are arbitrary constant, arbitrary scalars, I can choose whatever value for them that I want. I'm going to choose them to be what? Number one, right? Because right here is an invisible one. So, yep, let's do that. Let C equals D equals 1. And I plug it in. And yeah, that's it. I have property 2, property 1. Okay, if you have not proven line 3 yet, go ahead and try it now. Use basically the same trick. Press pause and come back when you're done. Welcome back. Let's prove line 3. Line 3 says that I'm given property 4 again, and I want to arrive at this line, T of CU. What do you think? What values do I choose? I choose whatever to make the dv go away, right? Because that's the only difference here. So let d equals 0. Then the dv goes away and plug it in. The dv goes away. I have cu left on the left-hand side, and this whole term goes away on the right-hand side. I'm good. So, yep, I have proven all 3 lines, and therefore I have my theorem. My theorem says that property 4 is true for any linear transformation. And in fact, it could replace both of 1 and 2, right? Because it's all equivalent. It's linear if and only if, right? So it's just as good. The single property 4 is just as good at both properties 1 and 2. It's so good, I'm going to copy it down again down here. Set the box set up, and I'm going to give it a name. Well, I didn't. Everyone else did. It's called the superposition property. And it has awesome applications in physics and engineering. And in fact, this can be generalized to more than just 2 vectors. If I have a linear combination of a whole bunch of vectors, I can expand it all out. Or vice versa, if I have a linear combination of a whole bunch of images, I can combine them together back to the original linear combination. Box it up, and that's a superposition property. All right, let's do one more example before we go into the last part of the video. Let T going from R2 to R2 be defined by that formula. Is T a linear transformation? Press pause and come back when you're done. All right, welcome back. Did you get no as the answer? This is not a linear transformation. If you didn't get no, if you somehow thought that it's a linear transformation, check your work. Okay, press pause, check your work, and come back. Okay, welcome back. Now that you know that the answer is no, let's start out with that answer is no. And the quickest way of saying that something is not a linear transformation is to use property number 3, the one that says if you start with 0, you have to end up with a 0. If you start at 0 and you don't end up with 0, you're not a linear transformation. Okay, that's usually the quickest one. There are some exceptions, but that's usually the quickest one to prove that something is not a linear transformation. So what does this transformation T do to the 0 vector? T of the vector 0, 0 is, by applying this formula, it is 0 plus 1 here on top and 0 at bottom. x plus 1 on top and same y at the bottom. And this is not the zero vector. And therefore, T is not a linear transformation. By the way, if you look at that x plus 1 y vector, it can be split into two vectors like this, xy plus 1, 0. And you can see that this is very similar to that example we did earlier with g of x is equal to 2x plus 1. It is this plus 1 here that messed up our linear transformation, that caused it to not be a linear transformation. Same thing here is because of this addition here. So in the world of linear transformations, addition of constant vectors is very troublesome. If you see something like that, go in the direction of trying to prove that it is not a linear transformation. That's answer number 1 by using property 3. Another possibility is to directly check with the original definition using property 1 and property 2 and see if they both work. If they don't both work, if one of them fails or both fails, then the transformation is not linear. If you haven't done it that way yet, go ahead and try it. You want to practice using different ways of proving the same thing to get good at this. So press pause and try that. Come back when you're done. All right, welcome back. This would be my answer to is I'm going to check property 1, the additive property. If I have a sum of two vectors, x1, y1, x2, y2, then this is a sum of vectors. I can add them together. And the T transformation is defined as add 1 to x and leave y alone. So it's that vector. Whereas what happens if I add the two transformations separately? If I have this plus that, so this is the left-hand side of property 1, this is the right-hand side. This one is equal to x1 plus 1. And this second transformation is x2 plus 1 like that. And I can add these two vectors together normally. And nope, they're not equal. And since they're not equal, T is not a linear transformation. I can do the same thing with property 2 as well. I don't have to, right? T's already failed property 1. But just in case you did property 2, I'm going to do property 2 now so you can check. I'm going to see if property 2 is satisfied. T of C times some arbitrary vector xy. Constant times a vector. I multiply the constant times every single entry in that vector. And by the definition of what T is, I'm adding 1 to the x position and leave the y position alone. The left-hand side of property 2 is that. Now I'm working on the right-hand side. C times T of the vector. C times is still C times. And then this transformation is equal to x plus 1 and y. And again, I multiply scalar times a vector. And nope, these are not equal as a general rule. It's only equal if C equals to 1, but it's supposed to be equal for all C, so no, not equal. Again, T is not linear. All right, let's go to our third part of this video, and that is to find the geometric meaning of a linear transformation. If you're given a linear transformation, how do you figure out what it does geometrically? Let's go back to the first example we did in this video. This one. I was able to figure out that this matrix multiplication, which we now know is a linear transformation, flips a vector across, like creates an image of it that is symmetric across the x-axis. Right? I was able to figure that out by applying that linear transformation to a generic arbitrary vector xy. So that's one way of doing that. If I'm given a linear transformation Rm to Rn, and I want to know what it does geometrically, there are two ways of doing it. Number one, I could compute the transformation T applied to some generic vector x1 through xm and see what it does and see what it looks like in Rn. That's what I did in the first example, in the opening example. I want to show you a second way of doing this. The second way of doing this is to compute T on each unit vector and see where the unit vectors are, and then look at the combination at the end and see what it does. Right, let me write it down first and then I'll explain it, and it makes a lot more sense. Compute T of each unit vector, T of 1, 0, 0, 0, 0. Then T of 0, 1, 0, 0, 0, 0. All unit vectors, the x unit vector, the y unit vector, the z unit vector, and whatever else, all the way to the last unit vector, 0, 0, all the way to the 1 at the bottom. And then you look at the combination at the end. All right, let me show you how this works. Let's take this example. T is a transformation from R2 to R2, where you take any vector in R2 and you multiply it by that matrix. And as we know, a matrix multiplication is a linear transformation. I'm going to compute the T of the first unit vector, the unit vector along the x-axis. That will be 1, 0. And then I'm going to compute the T transformation of the unit vector along the y-axis. That's 0, 1. All right, go ahead and compute that. This is just straight matrix multiplication. So press pause and compute. Come back when you're done. All right, welcome back. T of the x unit vector is equal to this matrix times the vector 1, 2 times 1, 0 is 1 times 1 plus 2 times 0 is 1. Second position, 0, 1 times 1, 0 is 0 plus 0 equals 0. I'm going to put it down here. Right, that's the transformation of the unit vector along the x-axis. The transformation of the unit vector along the y-axis is, and I multiply this out, I should get 0 plus 2 is 2. And in the second position, 0 plus 0 is 0. Now let me show you what to do with this information. the original space, xy space like this, I have the unit vector along the x-axis and the unit vector along the y-axis, and it makes for this little square. Whereas after the transformation, end up with 1, 0, which is this vector, but the other vector is not 2, 0, 2, 1. This is 2, 1. 0 plus 1 is 1. The other vector is 2, 1. So it becomes that vector. Therefore, this little square here becomes this little parallelogram there. So geometrically, it tells me that I started with this square and it got kind of like pushed over to become that parallelogram. This operation is called a shear. It's a pushover, slanted pushover. Those of you who have worked in graphics probably have seen this. Let me show it to you on Photoshop. So here on Adobe Photoshop, I have the map of Africa with the grid, and I put the grid in there so you can tell what's happening horizontally and vertically. And looking at the layers, actually, I have 2 layers of the same map. Okay, I'm gonna work on the top layer, and so you can compare it with the bottom layer that's not going anywhere. All right, so in Photoshop, shear is in filter, under filter, distort, shear. Right, and then this has thing that tells me how to shear it. I can shear it by a lot, by little. So I define my shear is slanted to the right, just like my the parallelogram that I got on paper. And I hit OK. There we go. So that's the shear. And we were able to figure out by taking the original unit vectors that makes a little square and figure out what happens to each unit vector, and based on that, figure out what our final answer is geometrically. So here's a summary of the definition and properties of linear transformations and how to figure out the geometric effect of a linear transformation. And that's the end of the lesson. Hope that helps. Any questions or comments, or any work you did that was not the same as the answer I gave you? Put in the comment section below. Like, share, and subscribe for more contents. And thanks for watching. Bye.